LR Parser. LR Parser is an example of bottom-up parser. Here, L stands for left to right scanning. Say for example, we have a string hello. So if I say that it is scanning from left to right, so the first symbol it would scan is H, then E, then L, then O. If I say that it is scanning from right to left, then the first character it would scan is O, then L, then E, then H. So this scans from left to right. Here R stands for rightmost derivation. Say for example, we have a production here AA, and here we have something like this. So if we open this like this, it is called as rightmost derivation. Why rightmost? Because I chose the right A to open or to expand. That's why it is called as rightmost derivation. If I chose the leftmost part for deriving, then it would be called as leftmost derivation. So LR parser uses leftmost derivation, means this one. Types of LR parser. LR parser is of 4 types that is in our syllabus. LR0, simple LR, canonical LR, look ahead LR. All of them uses the same algorithm. The only difference between this is in the construction of their LR table. So there is only minor difference between the construction of the table. Rest the algorithms are same. Here 0 and 1 means the look ahead. What do you mean by look ahead? Look ahead means that number of tokens it can read at a time. Number of tokens it can read at a time. Steps to create the parse table for LR0. These are the 4 steps that we need to follow in order to create a parse table for LR0. The first step is to augment the grammar. Second step is to draw the canonical collection of this particular LR item. Third step is to number the production, and fourth is to create the parse table. Just remember these steps. We are going to follow each and every step, and we would be creating a parse table. Taking an example. So let's take an example of a grammar. So first step is to augment the grammar. Augment the grammar. So augmenting the grammar means that we are just putting a dot in front of every production, and we are creating a mirror of start symbol. So this is the first step that we need to follow for every LR parsing table. Okay, so we just put a dot in front of every production. Here dot indicates that the production has been parsed or not. Say for example, I say that A dot B. Here it means that A has been read successfully and B is not read. A is read and B is not read. Okay, if I say that AB dot means that both A and B have been read. If I say that dot AB means that both AB has not been read. Okay, I hope augmentation is clear. Let's move on to the second step, where we would be drawing canonical collection from this particular augmented grammar. Okay, so here we would rewrite this particular augmented grammar like this. Okay, now if we want to read something, if we want to read letter or read a variable, we call this action as shift. Okay, so if I want to read S, then I would call shift on S. So it would look something like this. So here you can see that the dot is at the end of this particular production. That means that it has successfully been read. Similarly, we would shift A. Shifting A will give us A dot A dash. Here you can see that we have successfully read capital A and capital A dash is still left. So because we are getting a variable just after a dot, we have to rewrite that production. Here the catch is, if we are getting a variable just to the right hand side of a dot, then we have to write that production. Now we will shift small a. On shifting small a, we will get A dot A. Here you can see that we still got a capital letter value, that is A. So we have to again write it here. And we would shift to B. On shifting to B, we would get A dash B dot. Here you can see that we have successfully read B. So it can be called as complete state. Now you can see that this and this state has not been completely parsed or completely read. So we have to again shift it. Okay, so we would again shift it. Shifting it will give us A dot. So now you can see that the dot is at the end of production. That means that it has completely been read. Okay, now again we would reduce this particular production. Now you can see that it is at the end of the production. That means that it has been completely read. Now you can see that this particular production can go to this particular state in order to read small a. Okay, so we would go to this particular state in order to read small a, and this particular state will go to this particular state in order to read small b. So now you can see that all of our productions has been completely been read by our parser. this is completely red, this is also red, this is also completely been red, this is also completely been red. Since all the production has completely been red, we can say that our canonical collection is complete. Now we have to move to another step where we would be creating a parse tree using this particular canonical production. Till now we have learned that how to create a canonical collection of LR0 item using an augmented grammar. Now we will take an example and understand how to create a parse tree using a grammar. Let's take a normal grammar. S gives A and A gives B. Okay, so first step is we have to augment it. In augmenting, it would move it would look something like this. So we have successfully augmented a particular grammar. Now let's frame the parse table according to this particular grammar. So parse table contains two sections. First section is called as action and another section is called as goto. In goto we mention the variables. So what are the variables? Let me write the variables here. The variables are the capital letters that we use in our grammar. So variables are S and capital A, right? Terminals are the small letters that we use in our grammar. So what are the terminals that are in our particular grammar? That is P. Okay. In action, we write the terminals and we write the dollar. Okay. So now we have successfully created the parse table. Now we have to fill the parse table according to this particular canonical item. So let me shift it. So on shifting the value on S, it would go to S dash dot, right? So it means that it has successfully read this particular S. Now on reading the value of A, it would move to A dot. That means that it has successfully read A and it can be called as reduced. On reading B, this particular production will be get reduced and it can be said as reduced now. Now let me number this production. Let me number it. This is first production, this is second production. Okay. Now we would fill this particular table using this particular canonical items. So you can see that this is a 0 state, I0, okay, I can recall as I0, I1, I2 and I3. So total we have 4 states, 0, 1, 2, 3. Okay. So here we have to do the first step, that is we have to write except here in the name of dollar. Okay. Now we have to go step by step. You can see that I0 on reading B is getting reduced here because it has completely been read. So we would write here R2. Why R2? Because the production number is R2. Okay. Similarly, the production I0. This I0 on reading capital A is moving to I2. Okay. I0 on reading capital A is moving to I2. That's why we would write here 2. I0. Now all the shift and reduce of I0 are complete. Now we would move to I1. I1 is accepted, so we don't have to do anything. Now we would move to I2. I2 we have to, because it is a reduce move, then we would write here R1 because it is reduced. And why we are writing 1 here? Because it is the first number production. Similarly, we would write R2 for I3. Why R2? Because it is the second number production that we had numbered here. R stands for reduce and shift or S stands for shift. When we have completely read all the string, then it is said to be reduced. When we read one item, then it is called as shift. So this is the complete table that we have created using this particular augmented grammar. This parse table will be further used in order to create a parse tree using stack that we had previously saw in previous videos. So this is how we create a parse table using a augmented grammar. What is the main difference? In LR0, we write the reduced in whole row. You can see that I have written R1 here and R1 here. So whenever we are using LR0, we would write the reduce in whole row. This would be the main determining factor. In other scenarios, other parsing tables, we won't be writing reduce in whole row. We would be writing only in follow or in other criterias, but in LR0 item we write the reduce in whole row. So this is how we create a parse table for LR0 item. Types of conflicts. There are two types of conflicts, shift reduce and reduce reduce. So what do you mean by shift reduce and reduce reduce conflict? Say for example, I have been shifting a variable a and it is also being reduced somehow. It is being reduced also and it is being shifted also. So you can see that on reading A, it is shifting to this, and on reading capital A, it is getting reduced to this. So you can see that this particular state has a shift reduce conflict. If a state is having to reduce, then it is called as reduce reduce conflict. So for example, if I say that like this, so you can see that two productions are getting reduced on reading small a. So we would say that this particular state has a reduce reduce conflict because two productions are getting reduced. Whenever there is a reduce reduce conflict or shift reduce conflict, then we can say that that particular grammar can't be parsed. Okay, so whenever there is some conflicts in particular grammar, then we can easily understand that this particular grammar can't be parsed by our parser, and we have to use some other parser in order to parse that particular grammar. I hope all the points were clear to you, and if you have any doubts, you can comment down below. Thank you.